Just like displacement, velocity is another variable that can change as time goes on. And just like we did with displacement, we can track that on something like a graph. So now we can talk about velocity versus time graphs, and we'll look at one specific example. So you'll notice that this graph looks almost identical to the one that we started with on your displacement time graphs note, and it still has the exact same shape, and it still uses time on the x-axis as the independent variable, the thing that just keeps ticking away. But now our y-axis, our dependent variable, instead of displacement in meters, it's going to be velocity in meters per second. And even though the shape of this graph looks the same as our displacement time graph from the previous note, we're going to see now that the shape of this VT graph is going to tell us very different things than the displacement graph did. So first off, we start with the graph starting point. It's y-intercept. So that's this point right here. And we don't have specific values on this graph, so we don't actually know what that y-intercept number is. But we can definitely see that it's not 0. And that's important to make note of. So velocity here is not equal to 0. That's something we can definitely say for sure. And that's an important thing to make note of because it tells us something about the object. It tells us that when we started tracking this thing, when time was 0 seconds, we know that this thing was already moving. From there, we see that the line goes upwards. So it had some velocity that it started with, and then if the line goes up the v-axis from there, that means we're getting larger and larger positive velocities. So if we're getting bigger velocities, that must mean something is speeding up. And the technical term for that is we'll say that there's a positive acceleration. So I'll just use the vector symbol for A to represent acceleration. But a positive acceleration really just means you are speeding up. That's what we are really talking about. So it's a positive acceleration indicating that the object is speeding up at that stage. And then the line flattens out in the second or middle stage of this graph. So when it was a dt graph, that actually meant that the thing stopped completely. Now on a vt graph, though, we can't say that the thing stopped because that would mean that velocity was 0. But what we can say is that the velocity has flattened out or leveled out in a way that is producing constant velocity. The velocity is not changing. It's staying at the same level the whole time. So this part here is indicating constant velocity. And then from there in the final stage, it decreases. So notice that it still stays on the positive side of the y-axis. All of this is on the positive side of the y-axis. So all of these are positive velocities. But now we're getting smaller and smaller values for those positive velocities in the last stage. And so that must mean it's slowing down. So this stage here, we would technically call it a negative acceleration, which technically means you are slowing down. It's also good to point out what's happening at the very end as well. So notice at the very end, when this thing gets down to the very bottom, it eventually reaches a point where it touches the time axis. It gets all the way down to 0 velocity, and that's what that point means. So if it's down at a level that has 0 velocity, that must mean it's a point in time where the object ends up completely stopped. Looking at what we just did previously, let's see what we can write in general about what the direction of the slope and the steepness of the slope is telling us about a graph. Well, in terms of direction of slope, we could have two general possibilities. So we could have a slope that goes up in this direction, or we could have a slope that goes down in this direction. So if it's going up, we call that a positive slope. And if it's going downwards, we call that a negative slope. Those are our two basic options. And in this case, what are they telling us? Well, a positive slope we saw was speeding up. Whereas a negative slope meant that we were slowing down. Beyond that, though, the slope could be really steep or it could be more gradual or shallower. And so we need to make some sense of what that is telling us as well. So let's say we have a really steep slope up or maybe a really steep slope down. So if it's steep like that, that indicates a very quick acceleration. Because if it's very steep, it means that your velocity has jumped up very high with only a small amount of time going by. So if you're able to increase your velocity by a great, huge number in a small amount of time, it's because you've accelerated very quickly. The opposite to that would be if we had a very shallow slope going up or maybe a shallow slope going down. And that's the word that I use for a not steep slope, a very shallow slope. So that's the opposite, what we call a more gradual acceleration. And just like we did with displacement time graphs, it's useful if we actually take a look mathematically at what the slope of that line would tell us. So going back to basics, slope is rise over run, which technically means the change in your y-axis variable divided by the change in your x-axis variable. Specifically in our graph then, the y values are actually velocities, so it's some change in velocity divided by some amount of time that goes by. But we've seen that definition before. When we take a change in velocity and we divide by some time going by, we had a special name for that. We called that acceleration. So when we find the slope on a VT graph, what we found is the acceleration. Now, technically, if we're just finding the slope of a straight line, what we really found is the average acceleration of the object. And we can also show through unit analysis how this all works out as well. So specifically, we saw that our rise over run, or our slope, was taking our delta b and dividing by delta t. But if I want to think of what units that has, let's pull that off to the side and say, okay, the units for the change in velocity are just the units for velocity, which we always know are meters per second. And then I divide all of that by whatever the units for time are, which we always keep in seconds in this course. And so when that's the case, I'm taking meters per second, dividing that again by seconds. So if I put that all together in one unit, I get meters per second squared. So those dividing by seconds end up giving me 2 powers of seconds on the bottom of that unit. So I get meters per second squared. And where have we seen that before? Well, of course, that is the same units as acceleration. So not only does the rise over run tell us that it should be acceleration, when we do that same process with its units, it also tells us that the unit should match what we know about acceleration. So it truly is, when we find the slope on a VT graph, giving us the average acceleration of the object. So to finish off, we can summarize a few of the things that we found here. So when the slope is constant, or in other words, we have a straight line, we know that the object then must be undergoing a uniform or a constant acceleration. So whatever acceleration rate it's experiencing is staying the same. So constant acceleration. When the line is curved, though, that means the velocity is increasing in a nonlinear way. In other words, in a non-steady pattern. And that's because it's a non-uniform acceleration. And non-uniform is just a fancy way of saying not constant. Uniform is actually just a synonym or a word that means the same thing as constant in this case. So non-uniform just means not constantly accelerating. So the rate that it's changing its velocity is also changing as well. And those kinds of situations actually can get very complex, so we're not going to deal with too many calculations related to non-uniform acceleration. Most of the questions we deal with will assume that if something is changing its speed, it's doing it with constant acceleration rate. But if we did have a curve on a VT graph and we wanted to know its instantaneous acceleration, so how quickly it was accelerating at one instant in time, then we would use the tangent method that we used in our previous note. And we'll get some examples of this as we do some lab activities in class.